So now let us introduce the term entropy, and once we know what's entropy and it's a state function, then we can interpret second law of thermodynamics in terms of entropy also. So let us recall our Carnot cycle. So in Carnot cycle, there was two isotherms. So this is a point A. So first isotherm, it was at temperature T1 and then it is adiabatically compressed to temperature T2, as expanded, then compressed isothermally, then again it went back to this. So this was our Carnot cycle. So here the heat enters into the system Q1 at a source temperature. So T1 is the source and T2 is the sink, and the heat Q2 is rejected to this. So we derived the result that Q1 by T1 is equal to Q2 by T2. So this was what we derived the result, Q1 by T1 is equal to Q2 by T2, where T1, T2 are the source and the sink temperatures. This was what we discussed in Carnot cycle. So Carnot's engine is a reversible engine. Very important point, is a reversible engine. Now let us draw a general cyclic process. Let us consider a general cyclic process. This is the general cyclic process. So consider a general cyclic process. So now what we do, just imagine that so you see here what I have done. So you see here, this is a cyclic process, general cyclic process. I have reduced into a infinite number of Carnot cycle. You see, this is the Carnot cycle. This is going this way. The Carnot cycle. These two isotherms. So you see, I have divided into many type of isotherms. So these are the isotherms with different T1, T2. So this is T1, T2, T3, T4. Infinite number of isotherms and then infinite number of adiabats. So we have divided into infinite number of Carnot cycle. Now we divide the cyclic process, the general cyclic process, into infinite number of small Carnot cycle at different, working at different temperatures T1, T2, T3, T4. So the idea is to approximate a general cyclic process into infinite number of Carnot's cycle. Now you see here, let us use this relation. So here Q1 and Q2, I wrote their magnitudes, but if I write with sign, you see this is positive sign and this is negative sign. So I will get, so for heat entering, I will get Q1 at T1. Next, suppose at T2 it enters Q2 at T2, then again T3, it enters Q3 by T3. So plus dot 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 dot, so Qn plus Tn is equal to 0. Why? Because if I put with sign, this result with sign gives Q1 by T1 minus Q2 by T2 is equal to 0. So if I write these terms algebraically with sign, the total result should be 0. If I summarize this, I will write sigma QIR by Ti equal to 0. That is, I can write this as dq. So we can further write it as sigma dq reversible by T is equal to 0, where dq is the small amount of heat coming in that small processes. So if anything in a cyclic process, becomes 0, that means that must be a state function, because any state function in a cyclic process must be 0. So thus we introduce, let us write this, thus here we can introduce a quantity called ds or delta s, ds, which is dqr by T, so that integral that ds is 0 along the cyclic path. So thus we have defined a new quantity. Thus we have defined a term called S such that during a cyclic process integral ds is equal to 0. So S is a state function. Say exact differential, state function. This quantity S is called entropy. So like internal energy, entropy cannot be measured, but the change in entropy is measured. We define entropy ds or delta S as dq by T. Remind, this is reversible. So ds is equal to the change in entropy is measured and it is equal to dqr by T, and thus entropy is a state function. Now let us see this entropy and temperature and entropy diagrams. So suppose let us plot temperature versus entropy graph for a Carnot cycle. So this is our Carnot cycle, and I wish to calculate plot this TS diagram. T is here, entropy is here. Now you see, suppose I say A, B, C, D. So my first isotherm, is from A to B. So this line is represented as a straight line. Now you see here, the temperature is here constant and here isothermal constant. Heat enters. So when heat enters into the system, the entropy increases. So next, B to C, the process is adiabatic. Now you recall delta S is delta QR by T. So If there is adiabatic process, this quantity is 0. So ds is 0. So there is no change here. So you see this curve will be a straight line here. Then again C to D, the temperature is constant, and you see this was T1 and now this is T2. Also you can see the heat is rejected out of the system becomes cool, so its entropy decreases. Now D to A adiabatic process, again delta Q is 0. So you see this is the Carnot engine in TS diagram. So it is very easy to represent the Carnot cycle in TS diagram. Here diagram is very complicated, but here it is easy. Now this is TS diagram. You can see this Carnot engine expressed in TS diagram. So now very important point, you see when is the entropy decreasing and when is the entropy increasing. So A to B, when heat enters into the system, the entropy increases. So when, important point, when heat enters in the system, then entropy increases. Thus it indicates that it is the measure of randomness of the system. So when we give energy to the system, then its randomness is increasing, its entropy is increasing. Recall in our first discussion of the second law of thermodynamics, we said why work can be converted into heat 100% and why heat cannot be converted into work 100%. The result is work is a ordered form of energy. So the system is that where entropy is going to increase, the randomness. So in heat, the energy is in a random manner, but when we do work, we supply energy in a ordered manner. So randomness of the system is, so we say entropy is the measure of the randomness of the system. So this is another way of defining entropy, that more the entropy, more is the randomness in the system. Now again, let us come back to this portion. ds is equal to delta QR by T. So now let us see that if we have a TS diagram, then what is the area under the curve in a TS diagram? So now let us see, this is a TS diagram where entropy is plotted here, T is plotted here, and we have moved from here to here, A to B. So this is the area under the curve, and a similar diagram if I draw, so similar type of things we used to do in PV diagram. So A to B. So let us recall what this area under curve in PV diagram was. So area under the PV diagram was work done. So, and what in TS diagram? ds is equal to dq reversible by T. So we want T ds is equal to dqr. If I integrate this, I get as q reversible. So thus the area under the TS diagram gives the heat absorbed by the system. So it may be absorbed or rejected depending on the value. Similar to the area under the curve in PV diagram is given by work done. So what is work done in PV diagram? is Q in TH diagram. So area under the curve in TH diagram represents the heat absorbed by the system given by to the system, and W the work done by the system in PV diagram. So next we will see the law of principle of increase of entropy. So we have observed that in an isolated system the entropy will be always increasing. So this is called the law of increase of entropy, law of principle or principle of increase of entropy. So this is a very important statement. According to the principle of increase of entropy, the entropy of an isolated system either remains the same or ever increases. That means we can say this is another way of expressing the second law of thermodynamics. That means any natural process will change in such a way that its entropy should be always increasing, provided that system is an isolated. So this is called the principle of increase of entropy.